Hey everyone, we've done induced currents and induced EMFs from changing magnetic fields and changing areas, but the one thing we haven't really talked about much is the change in angle. So that's where a motor or a generator comes in. So in the case here, you're seeing that if I can get a loop of wire to spin in a magnetic field, this should change our flux and induce voltages. So in this case, the magnetic field is from the north to the south, the area is the area of that loop, and the angle between them is the only thing that is going to change when you spin that loop. Now to spin that loop, someone's got to do the work, so you're not getting energy for nothing. So in our case, we burn coal or oil or have nuclear reactions. In power plants, we heat water. Water turns into steam, and that steam turns into a turbine and spins that loop in a magnet or spins a magnet in a coil of wire. So either way, you can create and generate energy. But the main thing is you got to get that wheel to spin. Because before, whenever you have the area, let's say, in line with the magnetic field, you have the area pointing straight out, you have the magnetic field straight out, this is maximum flux. And as you spin that loop, the loop then goes parallel with the field. Remember, the area points 9 degrees away from the surface, so the area vector is pointing up, the magnetic field is now to the right, flux now equals 0. So if we're going to find the induced EMF, that's just the derivative of d flux dt. Now remember that flux is the number of turns, the magnetic field strength, the area, so far all three of these things are staying constant, but since it's a dot product, remember it's times cosine theta dt. Angle is changing as that wheel spins through there. And the wheel is spinning at a particular omega. And remember, in the relationship between omega and theta, omega is theta over time. I can rearrange the equation and solve for theta and substitute in an omega t. So now I have something changing with time. I have the theta changing with time. So what we need to do here is take the derivative of cosine omega t with the constants out front. And this is the induced voltage we get when we change the angle as time goes on. So it's NBA omega sine omega t, where the derivative of cosine becomes negative sine, and we get rid of that minus sign. So if you want the magnitude of the induced voltage, the maximum voltage will occur when theta equals 90 or 270, and we get minimum voltage when the angle would be 0, 180, or 360. When we generate electricity by spinning a magnet or spinning a coil of wire in a magnetic field, what we create is a sinusoidal voltage with time, which means we get a potential across the loop in one direction, so we get induced currents one way, and then about half of a cycle later, we get an induced voltage in the other direction, which means we have currents now in the opposite direction, and then it goes back and forth and back and forth. So what this generates are induced currents going in two directions. This creates what we call alternating current. Everything we've talked about in our circuitry has been direct current, so there's got to be ways to transform alternating current into direct current, and we'll talk about that a little bit later. But the setup also can work with motors. Remember, in the DC motors here, we had current flowing in one direction, we put it in a magnetic field, and that whole wire felt a torque. So it felt the need to rotate. And then we got to straight up and down, we said there was no torque, but the loop now had momentum, so it's going to carry it through. And if we didn't turn the current off like we did on our motors, we would see a torque in the opposite direction now, which would slow our wire down and our wire would oscillate back and forth. So our option at the time was just to cut the current. We turn the current off, allow that spin to continue, it would rotate till we're back to this scenario here, and we get the torque again. We get the kick again when the current comes back on. But one of the solutions people came up with was, we said, why don't we just switch the currents? When we get to this location, switch the currents and have current going in and current coming out, just like we had in the beginning. That would give us forces in the same direction that we had in the beginning, which would continue the twisting and it would keep spinning that loop in the same direction. So this is what we mean by an AC motor. An AC motor uses alternating currents that switch at the right time so that you can get that loop to continue torquing and spinning, and then attach that rod to the end of a shaft and have that shaft do some work for you. So to do the electric generation here, we've got a magnet we've got a coil of wire. You can see there is flux because there's field passing through the area, but there's nothing going on with the light bulb. To create electricity and create currents in that light bulb, we need this magnetic flux to change. Well, the area is not changing, the field strength isn't changing, but we need this angle between the magnetic field and the area to change. So that's why you start spinning the magnet, or you can spin the loop, either one, and you can see we get currents in one direction, then we get currents in the other direction. This would be an AC current. If I want to generate higher voltages or higher currents based on that omega NBA, all we have to do is have a larger magnetic field, a larger area, more turns, or faster changing angles. So you can see with a hydroelectric plant and a large waterfall, all they do is use the gravitational energy to spin the magnet or spin the loop of wire, and you create these alternating voltages and alternating currents. But when we looked at motional EMF, we said that moving conductors in magnetic fields create magnetic drags on the changing flux. So I've got a couple of demonstrations here for us. First demonstration here shows a permanent magnet with 3 different little spatulas, and if I move them in a magnetic field, they're going to feel magnetic drag. So I've got a solid spatula here, and as I drop it through the magnetic field, you see that it doesn't swing anymore. It was oscillating back and forth, but no matter which direction I try to send that spatula through the magnets, it always gets stopped. The second setup has some holes in the areas now. So they have, as some people said, less loops. So without it, the magnetic field, it swings pretty easily. In the magnetic field, it goes a little bit further. It almost makes it through, but there's still some magnetic drag. So how could we break up this magnetic drag? How could we stop these induced currents from creating drag? This last one, it looks more like a comb. There's openings at the bottom there so that you cannot have a complete loop. So it swings just like everything else, and then we put it in the magnetic field, and you can see that it swings freely through the magnet. And yes, it does die down a little bit, but at least it makes it through compared to the other two. I'll put both the one that has no loops and the one that is solid side by side, and we'll release them at the same time. And you can see the solid one creates a huge drag force. So those induced currents in the conductor we call eddy currents. It's just a hunk of metal, but you could create, like you see there, a small loop. And if that loop is in a magnetic field, it has flux. When I try to pull it out of the magnet, it has a change in flux. And it doesn't want that flux to change, so it creates what we call these little eddy currents that's set up in conductors. Circulate around the metal and try to resist the change in flux. To resist the change of flux, it's going to create a magnetic drag. And in this case, it's going to try and keep that conductor in the magnetic field. If it was outside and you try to push it in, the drag force would fight that change in flux and stop the conductor from moving towards the middle. And that's exactly what we just showed you in the demo. Another demonstration with eddy currents is this long aluminum pipe that I am showing you here. The pipe is hollow, so you can see there's nothing in the middle here. And since it's aluminum, it's not magnetic. I can put a magnet on it and it does not attract. Now the first time I saw this demonstration was on a Veritasium video, which I'll leave a link for, and you can watch the same thing I'm about to do here. But I'm going to take one mass and I'm going to drop it through the tube. We'll even time it. So there, I let it go, and you can see it's already out of the tube. From a top-down view here, you can see it takes really no time at all. But in my second demonstration, when I release the second mass, which is a magnet, I'm going to drop it through the tube now, and there's the start time, and I'm still waiting, I'm still waiting, I'm still waiting. There's the magnet. It took a lot longer for that magnet to make it through than it did the mass. You can watch it from a top-down view here. It's slowly going down that pipe. Now, why is that happening? Well, you can see the pipe as a conductor and a conducting loop for that fact. And a conducting loop, when it has a change in magnetic field, it's going to induce eddy currents in the opposite direction. Let me draw and explain what you're seeing here. So if I have a north pole and a south pole and it's falling through the tube here, remember there are magnetic fields that come out of the north pole and back into the south pole. So what we can see is we have areas that magnetic field is passing through. That means there is magnetic flux through those areas. Well, let's talk about that bottom circle. That bottom circle, as the magnet falls, the magnetic field is going to increase. And that loop's not going to want that to happen, so it's going to send its own magnetic field back up towards the magnet. And to do that, it's going to send current in this direction. So these induced eddy currents happen in the actual conductor, and remember what that does is it sends a tiny little north pole up and a south pole down. That causes repulsion and causes the magnet to slowly fall through the loop. Now at the top though, at the top you have a south pole, and the south pole is going away from that top loop. So the top loop's going to want to try and keep the south pole and keep the magnetic field going in the same direction, since that field's getting weaker as it falls away. And in that case, to throw magnetic field down, I've got current to flow in the opposite direction on the top end of this conductor. And remember, that creates a mini bar magnet with north pole down and south pole up. So the north and the south actually attract each other there, and that creates an upward force as well, trying to slow down that magnet as it goes through there. So watch it one more time. As the magnet falls down, you can see that there are these eddy currents that are created as the magnetic flux is changing, slowing that magnet down. Now I have one more extreme example with this. What it is a solenoid, so coil of wire right there, with a piece of metal through the middle to create a very large magnetic field. And here I've got a bunch of different rings that I can put onto that solenoid. When I push the button, it's going to send a very, very large magnetic field straight up through that solenoid. But since this is alternating current, that magnetic field is going to change from going up to down about 60 times a second. It's going to happen very, very quickly, which is going to create huge changes in flux for that loop. Well, that little ring, resisting that change in flux, will actually send its magnetic field against the change in flux, which will cause that little ring to repel itself up into the air. So here's a view from the bottom of the launcher. I push the button down and you can see it launches that little hoop up into the air. Now I've got a separate ring here. It's larger than the first one, so a larger area should create larger changes in flux. And that one went a lot higher than the first one. Now I also have a copper one. If I put the copper one on, copper one should induce really, really high currents because copper is a better conductor. However, it's a lot heavier, so it doesn't launch it as high. Now this last one I have, you can see there's actually a little cut in the ring. So if there's a cut in the ring, when I push the button, nothing happens. And the reason nothing happens is because there's a cut, we're getting no eddy currents and no induced currents to flow around. This last one is a light bulb that has a coil of wire on it, and when I put that coil of wire across this solenoid with the AC current, when I turn it on, it creates electricity. And that little light bulb is not attached to anything except has a changing magnetic field going through it. So like we said before, the drag forces is going to force the slab to either not come into the magnetic field or resist it from being pulled out of the magnetic field. And you can disrupt eddy currents like I did with that little comb, where I cut some of the metal out and I wasn't able to create very large loops of induced magnetic field, which gives me less magnetic drag. Which leads us to our last topic for this video, which we call self-inductance. What this means is that a current-carrying coil produces a magnetic field. This magnetic field passes through the coil and creates flux. So when we talk about flux, remember magnetic flux is magnetic field and area. If our area stays the same for a solenoid, then to change magnetic flux, I've got to change the magnetic field strength. And we're talking about a solenoid here, so magnetic field is just bunny. And mu0, little n, those are all constants. So really, I could say that the B is proportional to the current. The more current I have, the more magnetic field I have. With that proportionality, I could also say that the magnetic flux is proportional to current. So if we increase the current, that means we're going to increase the flux. But remember, what does that do for our according to Faraday's law. Faraday's law says that if we have a change in flux with time, then we're going to get an induced voltage. So if we keep changing the current with time, I will also be changing the flux with time. So what self-inductance says is that there's a constant of proportionality between the change in flux with time and how the current changes with time. And so we call that L. L is the relationship between the flux and the current. What L is, we call this the inductance. So the way that I can write this is that I can say change in magnetic flux with time is equal to negative L di dt, where L is the proportionality constant between current and flux. So what are the units of inductance? Inductance is flux over current. So if I want to look at this in terms of units, I get a Weber per amp, and a Weber per amp gives us one of our last units here, which we call the Henry. So resistance was measured in ohms, we have capacitance measured in Faradays, and now we have inductance measured in Henrys, which is Webers per amp. And since d flux dt actually equals the induced voltage, what I could say is the induced EMF is equal to negative L di dt, where L again is the inductance and di dt is the change in current. So if I want to solve for inductance with this formula, I can rearrange and get voltage over di dt. And if I want to look at that in terms of units, remember volt EMF is measured in volts, di dt is per coulomb per second squared. And if you do that, you'll actually also get a Henry as well. So I'll let you do the unit analysis there to prove that that also gives you the same unit that we had from before. So we've got this inductance thing. I've seen voltage over current before. So what it looks like is that the inductance is a form of resistance that resists the change in magnetic flux. And that's really what it is. An inductor is just a coil of wire or a solenoid that as currents are changing in it, it's going to create back EMFs or induce currents to try and resist the change in flux. So it's like resistance, but it only acts as a resistor when there's a change in current. So just like capacitors, inductors are only geometry dependent. Depends on how you create your coil. So it does act as a resistor while the flux is changing, but once the flux gets to its max amount, then the inductor is used to the flux and it's going to just act like a wire. So finding inductances may be complicated, but a solenoid we can solve the inductance very, very easily. The inductance, remember, is flux per current. And if I want to solve for that, remember flux is the NBA and current is just how many amps are flowing through that solenoid. But the magnetic field comes from the solenoid. So that's really mu0 little n I times the area, which again shows you that the current doesn't matter when you're making your inductor. All that matters is big N, mu0 little n, and the area of your inductor. And if we sub out what little n actually is, you get mu0 big N squared area over length. This is the equation for creating an inductor based on number of turns, and the more turns you get, you actually square that value, so you get a large inductance. The bigger the area gives you a large inductance, and dividing by length, the shorter the inductor actually gives you more inductance. Like a capacitor, the inductance is going to refer to how you make it. And if the inductor is filled with material, well then the inductance will change based on the properties of that material. Basically, you're changing the permeability of free space there. So that's self-inductance. We're going to use that heavily in the videos to follow here. So we'll talk then next time.